Assalamualaikum to Dr. Soba. We are from Group 5. We would like to present about our report on the topic application of thermodynamics, heat transfer and fluid mechanics in food processing optimization. The process that we choose is drying of flour. Before we begin, let me show you my group weeks. Drying is one of the most important steps in food processing industry, as most material used to create a food product contains moisture. For products like flour, the drying process is very crucial, as when it is come in contact with moisture, after a short period of time, there will be mold growing in the product, making it unsafe for public consumption. This report will discuss about comprehensive engineering principle of the convective drying process of flour. Experimental data was used in this report for the analysis, such as reduction of moisture content over time in the flour. The primary objective of this report is to apply the fundamental engineering principle including thermodynamics, heat transfer and fluid mechanics, as well as the equipment used in the drying process of flour. Another objective is to convey the practical application of this principle in a real-world context and to make food processing more efficient.
To maximize efficiency and quality in flour processing, selecting the right equipment based on operation scale and product thermal sensitivity is essential. Fluidized bed dryer are the gold standard for standard flour productions, because they suspend particles in an upward airflow, ensuring rapid, uniform heat transfer and preventing clumping. For massive industrial scales involving coarser material, rotary drum dryer utilize a tumbling cylindrical mechanism to achieve high output, but they are less suited for delicate specialty flours. When quality is the priority for high value and heat-sensitive flour, vacuum dryers are preferred as they allow moisture to evaporate at lower temperature under reduced pressure, effectively preventing thermal degradations. Conversely, spray dryers are used specifically to convert liquid slurries or powder emulsions into fine powder through rapid atomizations and evaporations. Finally, for laboratory research or small-scale batch processing, tray dryers offer a cost-effective and simple solutions. Regardless of the machine's reason, integrating heat recovery system and precise airflow control is vital to reducing energy costs and maintaining a consistent high-quality final product.
Next, we go for process description part. This drying process involves a simultaneous heat and mass transfer to reduce the moisture content of flour from 20% to a stable level of 40.2%. Initially, 1 kg of flour is packed in a thin layer to increase the surface area for drying. During the preheating stage, the flour is exposed to a steady hot airflow at 70 degrees Celsius with an air velocity of 1.5 meters per second. From 0 to 40 minutes, the process occurs in the constant rate period where the surface moisture evaporates rapidly. As a result, the flour mass decreases to about 0.970 kilograms. After approximately 85 minutes, the drying process enters the falling rate period. At this stage, internal moisture diffusion becomes the limiting factor and the evaporation slows down. The surface temperature of the flour increases and approaches 68 degrees Celsius as thermal equilibrium is reached. Finally, after 180 minutes, the flour must stabilize at 0.907 kilograms, indicating that the desired moisture content has been achieved and the product is still suitable for safe storage.
Next, for the data collection part, the experimental data recorded flour mass, moisture content, and the surface temperature at interval during the 180-minute drying. Next, for the first graph, the moisture content decreased continuously over time, and while for the second graph, the surface temperature versus time gradually rise and stabilize near 68 Celsius, showing thermal equilibrium.
For this section, the thermodynamics of the tray dryer were analyzed as an open system. Based on the first law of thermodynamics, the total heat demand was calculated at 2,409.93 watts. The key takeaway is that 2,250 watts are used solely to increase A enthalpy, resulting in a very low thermal efficiency of 4.4%. Furthermore, because the calculated demand exceeds the heater's 1,200 watt capacity, it is evident that the system was in a transient warming up phase and had not reached a stable steady state. In food processing, these values guide cost-saving decisions. To reach the 4.4% efficiency, two steps are recommended. Air recirculation can recover the 2,250 watts lost in the exhaust, lowering electricity use. Adding insulation also prevents the 100 watt loss through the walls. These changes help the dryer reach steady state faster and protect the flour starch and protein from heat-related damage while cutting costs.
Heat transfer is a fundamental process in food processing. It will ensure the food safety, extends shelf life, and enhances the product quality. There are three significant mechanisms, which is conduction, convection, and radiation. Conduction process is the direct contact and occurs when flour touches the hot surface, such as dryer walls and trays. can be calculated by using Fourier's law. Next, for the convection are the most crucial of heat transfer. Heat was transferred from air to flour particles that cause evaporation of surface area, and it can be calculated by Newton's law of cooling. Next, for the thermal properties, there are three properties. The first one is specific heat capacity, which is the amount of energy required to raise the temperature of flour, and it's known as its specific heat, which is Cp, and it is crucial to the drying process. Next, thermal conductivity. It controls how quickly heat travels through a material, and flour has a very low conductivity, meaning it will act as a good thermal insulator compared to metals or water. And the lastly is thermal diffusivity. It describes how quickly heat spreads through flour during drying and is defined as the ratio of thermal conductivity to the product of density and specific heat capacity.
Fluid mechanics is the study of how fluid substances like liquid and gases that do not permanently resist changes in shape to respond to various forces. This field is divided into fluid static and fluid dynamics. In a practical sense, fluid mechanics describe a substance through macroscopic characteristics like temperature, velocity, and density at specific locations. While some specialized fluids are isotropic, the most common fluids like air and water are isotropic, meaning they behave consistently regardless of the directions of the force applied. The primary physical difference between gases and liquid lies in their molecular arrangement. Gas molecules are widely spaced and move freely to fill any available volume, whereas liquid molecules are closer together, allowing them to flow and remain contained. This molecular behavior is a key factor in processes like evaporation, where molecules slowly escape from a liquid surface into the atmosphere. For the applications such as flour drying, fluid mechanics is essential for managing airflow dynamics to optimize heat and mass transfer by precisely designing air circulation systems. Engineers can ensure high evaporation rates that prevent the common issue of uneven drying. Ultimately, applying these principles allow for more efficient process that reduce energy losses and pressure drops, ensuring that the final flour product is a high and consistent quality.
Next, for the railway integration part, this section discusses how flour drying principles are applied in real industrial environment, focusing on optimization opportunities as well as practical challenge. In modern food processing industry, optimization of drying operations is essential to reduce energy consumption and ensure consistent product quality. One effective approach is predictive modeling. By using multi-variable data such as air temperature, airflow velocity, relative humidity, and drying time, machine learning models like artificial neural networks can accurately predict moisture content during drying. This reduces the need for trial and error operation and allows better process planning. Another important optimization strategy is the use of feedback control systems. These systems continuously monitor drying parameters and adjust air temperature, airflow rate, and humidity in real time. This ensures that drying conditions remain optimal throughout the process, preventing excessive heat input and unnecessary energy losses. Another one is adaptive drying schedule, further enhance efficiency by customizing drying profiles according to the characteristics of the flour, such as its initial moisture content, type of flour, and particle size distribution. By applying different temperature or airflow stages, drying can be completed faster while minimizing quality degradation. As a result of this optimizing strategy, industries can achieve reduced energy consumption, shorter drying times, and more uniform and stable flour quality. However, several challenges are commonly encountered in real-world application. One major challenge is case hardening, which occurs when high temperatures such as 70 degrees Celsius are applied too aggressively at the initial stages of drying. This causes the outer layer of the flour particles to vitrify or harden, trapping moisture inside. Although the surface appears dry, the internal moisture may lead to clumping or microbial spoilage during storage. Another major challenge is achieving uniform drying, especially at an industrial scale. In the laboratory, drying a 1 kg sample allows temperature and airflow to be controlled easily. However, in large industrial dryers can handle several tons of material, airflow is often uneven. This can create dead zone where the little heat or air reach the product. It's leading to uneven moisture levels and, in some cases, batch rejection. Lastly, fines entrainment is a fluid mechanics related issue in flour drying. Due to the very fine particle size of flour, high velocity air can carry particles out of the dryer through the exhaust stream. This leads to product loss and environmental pollution. To address this issue, industrial facilities commonly use cyclone separators or bag filter to recover fine particles and improve overall process efficiency.
In conclusion, this analysis successfully incorporated the thermodynamics, heat transfer, flow mechanics, and psychrometry principle in the process of drying flour. The data used show the reduction of material moisture content from 22% to 14.2% over the course of 180 minutes. The energy usage calculated is 2,409.93 watt, while the efficiency is 4.4%, which means the drying process is not efficient from the lack of insulation.